So thank you very much for your introduction. So first of all, I would like to thank the organizing committee and the chairman of the session for the possibility to give a talk here. So my presentation is about nanoscale organic and organic hybrids for multifunctional materials creation. So nanoscale organic and organic hybrids are attracting constant researchers' attention because they make possible to create materials with unusual synergetic properties. So the aim of our investigation was preparation of nanoscale organic and organic hybrids by surface modification. And we applied this powerful and versatile technique to two groups of objects. We applied it to for modification of porous inorganic nanocomposites, and we applied it to for modification of elementary organic polymer films. So for porous nanocomposites we used colloid chemical synthesis and mechanochemical synthesis, and for modification of elementary organic polymer films we used ion plasma modification. So as for the first group of objects, these are porous nanocomposites. These are nanocarbon nanodiamond composite and silicon carbide composites used as tablets, which are shown here on this slide. So some initial investigations were performed on unmodified or pure matrices, pure nanocomposites. So these are investigations on nanocarbon nanodiamond composite. This is the AFM image, and this is the X-ray profile. So the X-ray profile shows reflections typical for nanodiamond, and it gave rise to estimation of the grain size, that is about 4 nanometers. These are similar investigations for silicon carbide nanocomposite, also AFM image, and X-ray profile. So they had to be modified by organic chromophores. These are diarylethenes, so the aim was to create structures with possible sensing properties. So the chromophores are diarylethenes as they are suitable for detecting gamma irradiation. So they can exist in open and closed form. Open form is colorless, and closed form is colored. So under gamma irradiation, the open form comes into closed form, and it retains its initial state under visible light or UV irradiation. We also used spiropyranes. These photochromes are sensitive to heavy metal lines. In their open form, they change their absorption spectrum, and they can complex with metals, also resulting in changes in absorption spectrum. So we used these ones to modify nanoporous inorganic nanocomposites. We used colloid chemical synthesis, or in other words, impregnation methods. And for these ones, we used mechanochemical method, that is mixing with a mixture of silicon organic oligomers with subsequent covering the nanocomposite and curing this composition. So for modified and unmodified nanocomposites and their elements, some radiation investigations were performed. So it was shown that modified nanocomposites are stable under different types of radiation. Almost in all cases we we had radiation-induced luminescence, so that makes possible to use them as sensor materials. So modified nanocomposites are good precursors for universal chemo chip creation that can be installed into molecular electronic devices. So this chemo chip can be sensitive to both gamma irradiation and have a metal ion presence. As to another group of objects, these are elementary organic polymer films. We used both conventional and multi-layer monomolecular films. So these polymers, these silicon organic polymers were used as conventional films. This one is linear. This is polycarbonate block polydimethylsiloxane, or PCS for short. This is linear, and this one is cross-linked. This is a cross-linked PDMS containing special fragments or cavities that can be that can serve as centers of metal clusters growth under ion plasma modification. So we also used other polymers to use them as multi-layer monomolecular films. So we used polyamino acid cycle triphosphosine derivatives. These polymers are organic. These are also hybrid polymers because they have inorganic cycle triphosphosine core and they have an organic fragment polyamino acid chains. So these are hybrid polymers, CTPPAA hybrids for short, and we also used this alternating copolymer based on dihydroxypyridazole and isophthalic acid. So these polymers were used as monomolecular multi-layer films. So in this slide, investigation on PCS films are briefly summarized. So we used for metallization, we used copper, nickel, and gold. So as for copper coatings, they mostly show these coatings have in fact many defects, and one of them has monodispersed spherical particles because we have a linearity in Guinier plot derived from small angle X-ray scattering profile, and nickel and gold coatings form relatively smooth surfaces on polymer films with very few defects and with rather large defectless areas. So we have performed investigations on. I mean that as for previous slide, the structure of the coatings depends on metal chemical nature. So these are investigations performed on cross-linked PDMS with special fragments. From X-ray data, particle sizes and the volume fraction contents were derived. Normally, these are two particle. We have copper particles in the coatings, and mostly we have two particles fractions almost in all the cases. As for AFM data, the the starting films has grain structure with a grain size about 100 nanometers, with low treatment time, with low deposition times. We have curve structure with a curve size about several micrometers and a length of several tens of micrometers. And as for high deposition times, we have grain structures. This one, repaired in stationary mode, has a grain structure too, and it also has platelet structure. one can say that these grains are in turn from platelets. Well, they are not well shown. Shown here, one can see them at the image with a larger scale. So the structure of copper coating on this polymer film depends on strongly depends on deposition time. And these are surface pressure isotherms for polymers used as multi-layer monomolecular films. These polymers were transferred by Langmuir-Schaffer method onto quartz substrate for subsequent materialization. About 40 multi-layers were transferred onto substrate, and then they were metallized, so metallization conditions and roughnesses are presented here. So these structures, these multi-layer monomolecular films required I would say, softer conditions. So we used impulse mode that it provides lower heating of the substrate, about 30 or 40 degrees centigrade, so we can avoid possible destruction of polymers. So these are AFM images of CTP-PAA hybrid films. So in the unmodified, the undeposited film has grain structure with a grain size of about 100 nanometers, and ion plasma treatment results into island structure formation. So one can assume that metal has island structure on the polymer films, and different results were obtained for the polymer with a different chemical structure for pyridoxal just one isophthalate polymer. The starting films also has a grain structure with similar grain size, but modification by copper results not in island but in thread-like structure. But one can also see grains also of about 100 nanometers that are organized into quite regular threads. So here we have no island structure, we have thread-like structure. And some other properties were I would say useful properties were investigated for the structures. I mean electroconductivity, luminescence, and other. So many metallized copper coatings are luminescent in UV spectral area, and copper coatings showed no electroconductivity, which is different from gold and nickel coatings that show pretty good electroconductivity and could be promising for some electronic devices construction. So several conclusions can be drawn. So modified nanocomposites are promising for sensor materials creation and for element organic polymer films modified by metals. One can conclude that coating structure strongly depends on metal and on both metal and polymer chemical nature and polymer film structure, and these objects, these organic and inorganic hybrids can be useful for electronic or optical and some other devices construction. I would also like to thank Russian Ministry of Education and Science for financial support, some of my colleagues, and you for your kind attention. Thank you very much.
Any questions for Dr. Vantsyan?
Okay, I have many questions.
Okay, yes, please.
Not so many.
Because of audience. Okay, the first question relates to the problem of adhesion of these metallic films to the substrate, polymeric substrate. There is a big problem with this, of course. And I want to know something about this.
Yes.
And also about some mechanical properties or scratch resistance, for example. Because in such proposed application, it is very important also.
Yes, it's a good question, but unfortunately you haven't done yet any peel test. I know it's very important, and it's could be a bit difficult to make a peel test on multi-layer monomolecular films, metallized. So if you make a peel test, you can peel not only metal coating but also a polymer film, which is rather thin. It's about, well, its thickness. The thickness of one monolayer is about 1 or 1.5 nanometer.
Another question. What was the reason to select this polymeric substrate, just this one?
Polymeric substrate?
Polymeric substrate. Because there are many polymers. So.
You mean the choice
Yes,
of
yes,
a polymeric substrate? Yes, let me come back. Just a moment. So this one was chosen because it's biodegradable and biocompatible. So gold coatings or maybe silver coatings, we haven't done this yet, unfortunately, but they can be useful for biomedicine, for example. We have chosen this one, or with a cavity, but it's not a chemical, but I would say spatial syntron that may, I would say, catch a metal line or atom, but the role of this fragment is not yet understood. Maybe some modeling or some calculations are required for this one.
Chemically inert and low surface energy. So it's
yes, but it's not chemical. It's not chemical, but a spatial syntron. And we have performed a lot of investigation of polymers like this, and some quantum chemical calculations performed for phosphorescent fragments have shown the electron density on nitrogen atoms, and usually nitrogen-containing compounds have a large affinity to copper ions, because there are both organic and inorganic complexes with nitrogen-containing ligands with copper. And we have also performed some calculations on this one, but in fact on the fragment, and they have shown almost the same. So we have even 2 nitrogens here, and something like chelate complexes are possible. So this is the chip.
Well, then again.